Science and technological products are now ingrained in our daily life. We may even say that they're the invisible force behind the operation of modern society. How is the science behind these technologies born? How have scientists discovered and made use of the laws of nature to bring advancements to the world? What exactly is science? Today, let's take a look at 3 classic cases to see what insights they may bring us. So the story goes that once the Dutch merchant Antony van Leeuwenhoek invented the microscope, we humans began to discover all kinds of microorganisms around us, like bacteria and fungi. The scientists were mesmerized by the fascinating world of microbes, but at the same time also totally mystified by what they really were and where they came from. Most people believe that microorganisms emerged out of non-living matter when conditions were right. This theory is called spontaneous generation. Hey, look here. Clearly, these microbes come from rotting stuff. You just leave any food for long enough and you get bacteria from rotting. Meat broth gets stinky and milk turns sour if you leave them out for a few days. This is because they have rotted to produce bacteria. If you look under the microscope, even on non-living matter like a piece of paper, you'll see there are many microbes. So, I think microbes really come from non-living things. This is nonsense. Everyone knows that organisms come from reproduction of the same species. A pig gives birth to a piggy, a hen lays eggs that become chicks. If there is no former generation, how can there be the next generation? Even though the phenomena observed are the same, scientists often come up with different explanations for them. Those in support and those in objection to the theory of spontaneous generation all try to use experiments to support their stance. But no one was able to make any conclusion that could convince everyone else. That was until this man entered the scene. He is Louis Pasteur, the French scientist who had by then invented the sterilization method, now called pasteurization. I believe that microbes like bacteria do not come from non-living matter. Rather, they are afloat in the air, and when they land on food, they get the necessary nutrition to reproduce. If you were Pasteur, how would you test your hypothesis? If I could prevent food from being in contact with bacteria in the air, and if food kept under this condition does not turn bad, then it means that bacteria do not naturally come out of non-living matter. In 1859, Pasteur conducted just such an experiment. He put a pot of broth into 2 different flasks. One of them had an open top. For the other one, he heated up the bottleneck to bend it into the shape of a swan neck. Next, he boiled the 2 flasks of broth and just left them alone for 1 week. Guess what happened to the 2 flasks of broth 1 week later? Have they gone bad? The result was that the flask with the open top became stinky and mucky, but the broth in the swan neck flask was still clear. Why do you think that was? Because the broth in the open-top flask was in contact with a bacteria in the air, and therefore turned bad. But when bacteria and dust in the air entered the swan neck, They settled in the neck and were not able to get into contact with the broth. Therefore, this flask of broth stayed unspoilt. The experiment supported Pasteur's theory, which is the bacteria that would make a pot of broth go bad come from the air instead of from the broth itself. This is how, with rigorous experiment design, Pasteur refuted the theory of spontaneous generation. What do you think is the purpose of the open-top flask in Pasteur's experiment? If he had broken the swan neck from the flask, what do you think would have happened to the broth after a few days, according to Pasteur's theory? It is not just experiments conducted in a lab that count as scientific investigation. Through careful and systematic analysis of evidence, scientists can also formulate hypotheses to try to solve problems, thereby making contributions to the human race. From the 1830s to the 1850s, a terrible illness broke out in Europe. Those who became ill by it suffered serious diarrhea and vomiting. They would go into shock from dehydration and could die in the span of a few hours. In 1850, the disease broke out in London in the UK. The city was soon in panic as the death rate was very high, and yet no one knew what the cause was and how it was transmitted. As such, they also did not know how it could be prevented. This terrifying disease is cholera. Again, based on the same observations, people were making very different hypotheses about the cause of cholera. Some said that it was toxic bad air, caused by poor environmental hygiene. Others proposed that it was brought to England by goods and people from Asia. English physician John Snow chose to approach the deadly puzzle with statistics. He traced and analyzed the distribution of the cholera cases in the district of Soho in London by marking each case on a map. From this map, he observed some patterns. 1. Most cases lived around a street called Broad Street in the Soho district, and they were drinking from a public water pump on Broad Street. 2. There was a workhouse nearby Broad Street which had its own well. The inmates, meaning the people who lived there, did not drink from the Broad Street public well, and very few of them contracted cholera. 3. Nearby Broad Street was also a brewery, a beer factory. As their workers drank free beer, they also did not drink from the public well, and no one died from cholera. 4. Those who did not live around Broad Street but contracted cholera shared a commonality, which was they had all drunk from the Broad Street public well. From these patterns, how do you think the victims contracted cholera? How would you prove your hypothesis? Dr. Snow was convinced that the disease was spread by drinking water, and the public water pump was the source of the outbreak. So, he proceeded to convince the local Board of Guardians to abandon the Broad Street water pump. After the handle of the water pump was removed, the epidemic finally subsided. They later found out that there was a cesspit, a tank where human excrement was collected, just 3 feet from the Broad Street well. A baby who lived nearby had contracted cholera earlier, and her parents had dumped the water used to wash her diapers into the cesspit, contaminating the well. At the same time, without a proper waste system, many residents along the River Thames simply dumped their sewage into the river. Dr. Snow compared the statistics of cholera cases amongst users of 2 different water companies in London. One of them got their water from the Thames River upstream of London, and the other got their water downstream. Snow found that there were more cholera cases in families served by the second water company. Why do you think this was the case? Even though Dr. Snow did not know at the time what microbe might have caused cholera, with its detailed statistical data, in-depth investigation, close analysis, and rigorous reasoning, he was able to stop the spread of cholera effectively and became instrumental in making the authorities improve public hygiene and the city sewage system in order to protect their citizens' health. His work has since been considered the foundation of the modern study of public health. Because of this, he is called the father of epidemiology. One day in 1786, Luigi Galvani, an Italian anatomist, was dissecting a frog in his lab with the intention of studying how nerves control muscles in animals. His wife, Lucia, was his lab assistant, attending to his work. "Lucia, would you hang this up for me, please?"
Goodness me! This frog is revived.
"I have cut up countless frogs in my life, but never encountered such a thing." He then dissected a few more and hung them all on an iron rack, each by a copper hook. And guess what they saw? It's electricity. Benjamin Franklin discovered electricity in the air, and now I have discovered electricity in the frog. I am going to call this animal electricity. Galvani repeated his experiment under different situations and found that the frog's legs twitched with different intensities when they were hung on racks made with different metals. They did not twitch at all when they were hung on a non-metal rack. He finally published a paper in 1791 to announce his discovery of animal electricity. He believed that, like the electric eel, which can discharge electricity, the frog, or even human beings, can produce animal electricity in our brains and transmit it through our nerves to our muscles, making them twitch. Now, what do you think about his explanation? Do you agree with it? A contemporary of Galvani, an Italian scientist named Alessandro Volta, did not agree with him. In Galvani's experiment, he used copper hooks to hang his frogs on the iron rack. I believe that a low level of electricity is produced by the contact of two different metals, and thereby stimulated the frog legs to twitch. It is not the frog legs themselves that carry electricity. And do you agree with Volta's explanation of the phenomenon? If you were to test this theory, how would you do it? Both scientists had acknowledged the same phenomenon, yet each had their own explanation. They each conducted their own experiment to support their theory, not conceding to the other. After 7 years of hard work researching the problem, Volta finally achieved a breakthrough. He placed with a piece of paper or cloth soaked with salt water on top of a copper plate, further topped with a zinc plate. Then he repeated this pattern of copper plate, soap plate, and zinc plate again and again, assembling a pile that was connected to wire at the top and the bottom. I firmly believe that it is not about the frog's legs. It is a combination of different metals that discharges electricity. Let me make some more layers and I'm sure I'll get some results. This is what would come to be called Volta's pile. At last, when Volta created a pile of 50 layers, he was able to produce enough electricity to give people a shock. And when he reached 100 layers, as the two ends of the electric wire came into contact, they ignited a spark. It is in this manner that Volta created what became the world's very first battery. It was his doubt about Galvani's conclusion on the results of the frog experiments that motivated Volta to tirelessly repeat and refine his own experimental design. His skepticism led him to finally be able to overturn Galvani's animal electricity theory. But Galvani's animal electricity was not a total mistake. The neurons of an organism indeed rely on electrical impulses to transmit signals. And if not for Galvani's frog leg experiment, Volta might not have invented the battery. We have now looked at all three cases. Can you point out any commonalities among them? First of all, we can see that they all start with keen observation and the asking of questions. Then, based on existing information and knowledge, these scientists proposed their own hypotheses. And they tested their hypotheses through experiments or other methods. Lastly, they analyzed the results, plotted graphs to present the patterns in data if possible, and then drew a conclusion. If the evidence from their experiments supported their hypotheses, they would accept them provisionally. But when new evidence emerged and challenged the original hypothesis, then it would have to be amended or even rejected, just like how Pasteur refuted spontaneous generation, or how Snow refuted various speculations on the source of cholera, and how Volta overturned the animal electricity theory. It is very common in science that a theory gets refuted. It does not indicate failure. Rather, this is how the whole scientific community makes advancement. At the same time, rigorous experiment design and clear and open steps allow others to test and verify research results, also allowing the scientific community to move forward as a whole. It must be emphasized that while some basic characteristics can be observed in scientific methods, scientists use different approaches when confronting various problems. Therefore, there is not a single standardized scientific method. Science is a process by which human beings understand the natural world and the knowledge that we acquire from it. Aside from methods, there are also certain qualities that successful scientists often share, such as curiosity, honesty, humility and skepticism, as well as imagination and creativity. Scientists have a strong sense of curiosity. They look at everything around them with fresh eyes and have a strong drive to understand. They keep asking questions to try to find the truth. Science is based on evidence and loyal only to facts. Scientists examine viewpoints and matters with cautious skepticism, but they must also humbly listen to the opinions and viewpoints of others and accept new evidence, including those that might refute their own theories. Scientists must also exercise bold imagination and demonstrate an innovative spirit. It was with imagination that scientists James Watson and Francis Crick boldly hypothesized the double helix structure of DNA. Nevertheless, science is not all-encompassing or powerful. Science is a systematic method that allows us to investigate natural phenomena and processes in an objective way. Until today, there are still many questions left unanswered by science, such as the origin of the universe and that of life, or whether there is extraterrestrial life. In realms outside of nature, such as ethics, aesthetics, religion, and society, we all the more need to depend on other ways of obtaining knowledge to bring us insights.